Tuesday for you. I will be perfectly frank, it's still Monday for me. I'm just trying to knock these videos out in a row while I'm thinking about it. So, I asked you to calculate a whole bunch of moments of inertia, and I posted a solution set to that online. What you should have done is corrected yourself and then have posted your work on the Monday night assignment as I indicated in the Google Classroom post. But I want to go over a couple of things there in terms of pattern. So just to look at the piece of paper that we had here, I just want to bring back some stuff from yesterday and then go on to talk about some new stuff in this first video about point masses before we move to talking about continuous masses in the next video. So first, I want to point out some patterns. I want to first talk about this point here. Notice we have three axes, axis D, B, and F, that go through the same point. So if I go to my page here, that was axis B, axis D, and axis F. So what I want to recall for you is the perpendicular axis theorem, which says that the moment of inertia of the axis through the plane, which in this case would be axis F, should be equal to the two perpendicular axes that go through that point, which in this case would be B and D. So let's check it from our work. Axis B, 96 kilogram meters squared. Axis D, 48 kilogram meters squared, which is equal to, if we do this, did I get my numbers right? Hold on a second. Going back here, did I add all of these up right? Oh no, I did not, because this should be 36 and 36 is 72. This should be, 144, right? And if I add these up, these are indeed 144 kilogram meters squared. So check. Everything works out there. So perpendicular axis theorem, yay. So notice we said perpendicular axis theorem. I wonder if there's something called a parallel axis theorem. And there is, and that shouldn't be shocking. So let's look back at our picture. Notice here we have a bunch of axes that are parallel to each other. For example, D, A, and H are parallel to each other. D, A, and H. Now, if we look at that, their moments of inertia are D is 48 kilogram meters squared, A is 24 kilogram meters squared, and H is 120 kilogram meters squared. And those were all of our vertical axes, right? Now let's talk about our horizontal, oh my God, how did I spell that? Horizontal axes. And that would be, we had B and E, we only had the two. So B was 96 kilogram meters squared. E had a moment of inertia of, once again, 96 kilogram meters squared. Interesting. And then we have the ones through the plane. And that was C, F, and G. And so those were, C had a moment of inertia of 120 kilogram meters squared, F 144 kilogram meters squared, and G is 336 kilogram meters squared. So there's got to be some patterns there. Well, first I think we can see that the vertical axes generally have a lower moment of inertia than the horizontal, and which are generally smaller than the ones through the axes. Well, why is that so? Well, if you look at the distribution of mass, we said that moment of inertia is less when the distribution of mass was closer to the axis of rotation. Because this thing has a smaller width than it does height, it makes sense that from the vertical, more of the mass is probably going to be closer. Our outlier here was this, which is way outside the mass, right? Versus here, versus axis through the page where more of the mass is indeed further. Notice G had the largest moment of inertia because most of the mass is pretty far from point G. So that sort of gels with what we were talking about. But why then does axis A have the least, then D, then H? There's got to be some sort of relationship. Well, there's got to be something, an existence of an axis about which we have a minimized moment of inertia for all points, or for all axes that are parallel to one another. Meaning there's got to be some axis here along the verticals, which would minimize the moment of inertia along the vertical axes. There's got to be some axis along the horizontal where we get a minimum moment of inertia. Anyone want to take a guess where that would be? And if you guessed, based on our conversation from yesterday, that that would be through the center of mass of the object, you would be correct. So let's prove that, and then let's see how we can exploit that. So where is the center of mass of this system? Well, we got to find that because we don't know at the present moment. So if I'm finding the center of mass, I need to have an axis, 0, 0, and any declarations up and to the right are positive. Now, if I just took a guess here, very simply, 3 kilograms, 3 kilograms, 9 kilograms, 9 kilograms. We have a symmetrical structure. So I actually know that the center of mass is going to be along axis A. But because there's more mass to the top, it's going to skew upwards. So I actually don't have to do the XCOM calculation because I could just very simply say by symmetry, the XCOM position is 1 meter. But the vertical, that we're going to have to do. So let's do it. So XCOM is equal to 1 meter by symmetry. But YCOM, sum of the YMs over the sum of the M's. And here we go. So y1, m1 plus y2, m2 plus y3, m3 plus y4, m4 all over m1 plus m2 plus m3 plus m4. Sorry, my handwriting has got terrible there. The La Croix can is right there, and I didn't want to knock it over. So I'm going to move this over a little bit more. So notice the first two terms zero out, but I'm still going to have them there just so I don't forget to put the masses in the bottom. Plus 9 kilograms times 4 meters plus 9 kilograms times 4 meters all over 3 kilograms plus 3 kilograms plus 9 kilograms plus 9 kilograms. And I've got 72 over, what's that, 72 over 24, and 72 over 24 is a very nice 3 meters. And now I think you'll understand why I chose the numbers I did for the distribution, because it gives us a fairly nice, easy thing to look at. So let me go back to the original picture. There would be our center of mass point, 1 meter from here, and then 2 meters from here, or if I want to say 2 meter, or the 1 meter from here, and 3 meters up from our axis. Either way, what I want to do is I want to find a couple of things. So one, it looks like axis A for the vertical axes is actually going to be the lowest moment of inertia, 24 kilogram meters squared, right? Let's prove just that that's going to be minimized. Let's do an axis that's very close to that, but moved over slightly from there. So I will call this axis G, H, I. I don't want to do axis I. We'll do it axis J. So there we go. And we'll say axis J is just moved over by, oh, I don't know, 0.2 meters over from there, which is going to yield some kind of annoying numbers. So let's get to it. IJ, which is going to be 3 kilograms times, and that would make this 1.2 meters squared, plus 3 kilograms times 0.8 meters squared plus 3 kilograms times, 9 kilograms times 1.2 meters squared, and then plus 9 kilograms times 0.8 meters squared. Bear with me, folks, because I've been using my phone for my calculator, but I'm using that as my video. So here we go. That's so that's 3 times 1.44 plus 3 times 0.64 plus 9 times 1.44 plus 9 times 0.64. This is usually when I'd be calling out to you and asking you to do this calculation for me, so I don't have to do it in my head, but say la vie. There it is. Good. Plus, what's that? 2 went up, 1.92, and then this is just going to be 3 times what that one is. So 6, 9, 12, and this one is just going to be 3 times that one, or 6, wow, 3 times that is 7, 2, and 5. Good. And then we could put all that together, and that's, let's see, 4, 1 of 18, 28, 29, 9, 2, 6, 7, 12, something like that. Okay. I might be off about that. I can check my math later. But the important thing to notice is that ij is indeed bigger than ia, that we perturb the axis slightly to the right of the center of mass, and we got a larger one. Theoretically, I could perturb that to the left. Now, if I perturbed it 0.2 to the left, you'd see I'd actually get the same exact result because of our symmetry. We'll actually do a little bit of a proof later to show, or actually you will do a proof to show that it does minimize about the center of mass. That's a problem in the textbook that I'm going to assign you a little bit later. But there you go. But the thing is, I wonder if there's a pattern between all of the axes that are horizontal. So let's look at all of our axes that are horizontal. I have IA, which is 24 kilogram meters squared, and that's on the COM. I have IJ, which is 24.94 kilogram meters squared, and that's deviated, let's call that D, how far it's deviated from the center of mass, by 0.2 meters. And then if I look at, I don't know, D, that was 48 kilogram meters squared, and that's deviated from the center of mass by 1 meter, right? And then IH, which is, what was IH? 120 kilogram meters squared, and that was deviated from the center of mass by 2 meters. All right, so what we want to do is see if there's any relationship between all of these numbers. Now, normally I would just set this to you, and if you want to stop and try and figure it out, go for it. Stop the video right now and figure it out. All right, if you stopped the video and you tried to figure it out and you didn't get very far, or you got a little bit, let me give you a hint as well. The total mass of the system is going to be 3 plus 3 plus 9 plus 9, 24 kilograms. That's going to matter. Maybe stop now and figure it out. Okay, if you're back, I'm going to give you another hint. Every time we've dealt with a distance in this, we've squared it. So let's look at d squared. 0, 0.04, 1, and then this is 4. Maybe try that. Stop and figure it out. Okay, so now let's look at mass total of the system times d squared. 0. Let's see, 0.04 times this. Oh, well, that's conveniently 0.94. Or actually, so maybe that's wrong from the initial. Oh, I'm sorry. This should be 6. Excuse me, 6, because that's 0.96. That if we do 1 times 24, that's 24. 4 times 24 is 96. Anyone see it yet? Well, it looks like that the axis that is parallel is equal to the moment of inertia through the center of mass, 24, plus the total mass times d, the shifting factor between the axes, squared. And that, my friends, is called the parallel axis theorem. So let's check that out to see if it checks. Let's look at all the horizontal axes. Right now, I have horizontal axis E, but I don't know the moment of inertia through the center of mass. So let's find that. So if I do a horizontal axis through the center of mass, so going back to this picture, that would be this axis here, JK, right? We'll call that axis K, right? IK would be equal to 3 kilograms times 3 meters quantity squared plus 3 kilograms times 3 meters quantity squared plus 9 kilograms times 1 meter quantity squared plus 9 kilograms times 1 meter quantity squared, or 27 plus 27 plus 9 plus 9, which is, well, that's 54, 64, 72 kilogram meters squared. So that's our ICOM through our horizontal axes. So therefore, IE should equal IK, which is the ICOM, plus the total mass of what I'm using the parallel axis theorem on, times d squared. So that'd be 72 kilogram meters squared plus the total mass, which we agreed before was, wow, can't even remember, 24 kilograms. And then what is the shifting factor? Well, if we look at that, the shifting factor from the COM up to axis E is 1 meter. So I'll put 1 meter quantity squared there, and I get 72 plus 24, or 96 kilogram meters squared for axis E. And if I go back to my table, you will find that axis E is indeed 96 kilogram meters per second. You can try that about all the other axes if you want, just to verify that it's true. But the great thing about the parallel axis theorem is going to be we can take a very complicated system, and instead of doing the very complicated work by finding a moment of inertia about a center of mass, because most often that's going to be an axis about which there's symmetry through, we can use that to find the moment of inertia of very complicated systems when you're not doing things about axes of symmetry. And so that is our first video of the day. So what problem in the textbook am I asking you to do then based on this? Well, if we go to chapter 10, there is a question, and that is question 27. Let me show it to you here. Okay, it's this one here, and it's going to ask you to prove that the moment of inertia is minimized about the center of mass. So I will post a solution to that a little bit later today, and you should give it a whirl. Okay, bye.